To continue our talk about Manova, we had just finished this slide last time, so we'll continue on. You can also include covariates with Manova and have something called Mancova, which, as a side note, I believe was Barbara Tabachnik's stage name when she used to belly dance. I believe she danced in her Mancova. At least that was a story I was told anyway. Anyway, but just like Ankova, you're going to bring in, covariates to adjust for, you can adjust those linear combinations of DVs that we are creating with the Manova. You're going to adjust those for the presence of those covariates and actually hope to reduce some error variance and other things so that you can actually make the test more powerful in the best case scenario. So we can do that too. The basic requirements for a Manova are you need to have 2 or more DVs. Right? So up here you see that with an ANOVA you had to have 1. As soon as you get to 2 or more sort of continuous variables here, interval ratio, you now have to switch over to Manova. It now leaves the univariate realm and goes into the multivariate realm. Now you also need to have at least 1 categorical variable. Now this could be just a dichotomous variable, so it could be just 2 groups, and when you do that, that's called a tau squared. And as soon as you get to more than 2 groups, it's basically just like an ANOVA. You can have multiple groups and compare those groups on the linear combinations of the DVs. You can also have more variables, more IVs, and you can have factorial designs and all kinds of stuff that we'll talk about more later. If you're going to do a Mancova, right, if you're actually going to do this multivariate analysis of covariance, you also need at least 1 continuous covariate, so something measured interval ratio that you're going to try to use to control for some of that variability. So Manova advantages over ANOVA. So 1, Manova allows you to diversify. So diversification. So as you see there, that picture you see right here, this is a picture that's talking about don't put all your eggs in one basket. Whenever you run an ANOVA, you're actually doing all this work to bring people in, collect data, do some kind of research design, manipulate things. There's time and money involved. All kinds of stuff goes into research design. And when you have just a single dependent variable, your manipulation that you're doing, whatever your research design is, you're really putting a whole lot of faith in the fact that those differences, the manipulation that you're doing is going to impact just a single dependent variable. If that one dependent variable is not affected, is not changed, then all the effort was sort of for nothing. So what Manova allows you to do is to include a lot of, or at least a few dependent variables at one time so that you can see if your research design can impact any of them. And it may impact all of them. It may only impact one of them, but the Manova will allow you to sort of sort that out, and it allows you to diversify the impact that your IVs may have on a group of dependent variables. It also is more efficient in the sense of you're able to do lots of comparisons, lots of tests, all in one overall model, which makes it a lot more efficient design relative to ANOVA. It allows you to control for type 1 error. And by that I mean, if you were to try to do just individual ANOVAs, like multiple ANOVAs, each ANOVA would bring with it a 0.05 alpha level typically. And so each time you do another ANOVA, you're actually increasing the likelihood of making that type 1 error. If you do it with a Manova, you're actually able to do all those tests at one time for just one 0.05 alpha level, and help sort of control for that and make it it helps to reduce the inflation caused by multiple tests. And you can kind of tell if I'm actually spreading out that 0.05 alpha over multiple tests, it's likely, actually it's not just likely, it is, the power of the design is actually going to be lower relative to the individual ANOVAs. So there is a bit of a trade-off. There are rare times as well that when you run a Manova, it'll actually find differences between groups that any of the individual ANOVAs cannot find. And that's because as it's combining these dependent variables together, it's actually able to sort of maximally weight each of those dependent variables to create a sort of super component, a smart composite. And that might actually differentiate between the groups better than any of the individual ANOVAs might. So it's possible, it doesn't happen very often, but every once in a while you might come across a Manova that finds differences that you cannot find in any of the individual ANOVAs. Anyway, that's it for that slide. What kinds of research questions can you ask with a Manova? Well, the good news is they're essentially, at least these first here that you see, are basically exactly the same as that you would ask with an ANOVA. Are there main effects for each of your IVs? Looking at sort of like marginal mean kind of things with ANOVAs, you can actually have something similar with Manova. Are there interactions? Can you bring in covariance and help to reduce some of the error and run a Mancova? But additionally, sort of something extra relative to ANOVA, you can also ask questions like, well, which DV is or which DVs are most important? Because you have multiple DVs, when you find a significant Manova, you can then actually follow that up with either multiple ANOVAs to figure out where, like on which DV are the groups actually different, and figure which ones are important in differentiating between groups. And you can also do something called a Roy-Bargmann step-down procedure that will help you do that exact same thing, but also help to control for the correlations among the DVs as you go through and look for the relative importance. We'll come back to talking about that in a little bit. Just like with ANOVA, you can also ask about what are the parameter estimates? How do I estimate population parameters based on the samples that I've sampled, the people that I've sampled, and you're able to estimate things like marginal means. You're able to, if you're using a Roy-Bargmann step-down procedure, you can actually report the adjusted means because each time you're doing each subsequent step of a Roy-Bargmann becomes an ANCOVA, so each thing is being adjusted as you're going forward. And each of these parameter estimates are going to come with standard errors and confidence intervals, so you can report those things and actually get an idea of what the parameter estimates look like and how they might range in the population. You can also, the kinds of questions you can ask are, in terms of follow-up tests. If I have a significant Manova followed by significant ANOVAs, for any of those significant ANOVAs, I can ask, are there significant follow-up tests? So I can do things like post hoc. I can do plan comparisons, plan t-tests. I can do post hoc adjusted ones like with Chaffee or Tukey or any of the other dozens of corrections. Bonferroni. I mean, there's a lot of them. So I can do follow-up tests to try to figure out which groups are actually different from each other. And I can actually compute effect size. So the cool thing about effect size here is that we're going to get different kinds of effect size. As I run a Manova, I can actually get multivariate effect size, which is what the MV is there for. So I can get multivariate effect size, or I can actually compute univariate effect sizes. As I do the Manova, it's going to come with multivariate effect size estimates, and each of the univariate ANOVAs that are sort of come after the Manova will also have univariate effect size estimates as well. So what are the assumptions of Manova? So the good news here again is that the assumptions are essentially the same as they are for all of these general linear model type tests. So when we do, we talk about ANOVA, we talk about canonical correlation, even with multiple regression and all those things, we assumed a lot of the same things. We assume the data is normally distributed. We assume that they're linearly related. We assume things like homoscedasticity, or this sort of homogeneity of variance assumption. We assume a lot of those things because they're all part of this general linear model, which is basically the umbrella sort of mathematical sort of equation that covers all this stuff. So because of that, many of the assumptions are going to be the same. It's just they get applied a little different. Because we have multiple DVs, instead of looking at homogeneity of variance as a single as the variance on a single variable being the same across groups, I now have multiple variables. And not only do those variables have variance in each of the groups, they also covary with each other. So we're now going to expand that idea out to looking at whether or not the variances and covariances between DVs are the same across groups. We'll come back to that in a little bit. But it's the same idea as homogeneity of variance. It's just been expanded out. We're now thinking about them as matrices instead of as just a single variance estimate that we're comparing across groups. So before we think about sort of assumptions, this is, I guess, part of the assumption, but it's really, we're assuming, like in terms of theory, we're assuming in order for us to make any real conclusions, in order for us to look at the analyses that we've done and to say anything real in terms of conclusions about them relative to our theory, I really want to emphasize it's the research design that matters. Your research design, the stuff that you may be talking about in 692, or that you talked about in your research methods class in undergraduate, like Psych524, if you're an undergraduate here. The research design you use and how you actually control for things like internal validity and external validity and get rid of confounds and all those steps we take to have a really good experimental research design is what's going to impact your degree that you can make conclusions based on the analyses. So with that being said, we're now moving into sort of fancier statistics. We've gone from these sort of simple ANOVAs. We're now moving into Manova that's multivariate. And yes, the degree of complexity is increasing, but just because the analysis is becoming more fancy, it doesn't mean it's going to make up for poor research design. So you see here, fancy stats do not make up for a poor design. Now this is something I want you to see this, and I want you to think about these two things here, these two garbage cans. This is a saying you hear a lot in, actually a lot of places, but in stats in particular, you hear this idea of garbage in, garbage out. The research design is really what dictates the kind of information that goes into an analysis. So as you're collecting data, the input that you're getting, the measures that you're collecting, like your dependent variables, their quality really depends on how well the research design was done, how well the levels of your IVs were manipulated, how well you define those dependent variables, and how well you collected them. So there's both a research design component, but also a measurement component. How well were those dependent variables actually measured? All that stuff is going to impact how the data comes into your analysis. How the data is collected will impact how good the data is when it's coming in to your design. If what you put into an analysis is garbage, what you will get out of the analysis will also be garbage. So this idea of garbage in, garbage out means that what you put into analysis really impacts what you get out of it. And it doesn't matter, this little arrow, whatever the process is, whatever the analysis is that you're doing in between the data being collected and you interpreting your output, this doesn't matter in terms of you cannot make this garbage into something wonderful and something meaningful out here. If you have garbage going in, you're going to have garbage going out, despite how fancy or complicated or sophisticated your analysis is. It does not convert garbage into gold. You got garbage going in, you got garbage going out. So I want you to think about, remember those two trash cans, garbage in, garbage out, and like repeat to yourself at night when you're going to sleep, garbage in, garbage out, garbage in, garbage out. That you really need to spend more time, if you spend more time on your research design and your data collection process, you'll spend less time trying to fix things and trying to spin garbage into gold when in fact it's not going to help. So remember, garbage in, garbage out. Other things to think about is that as you're trying to select dependent variables to use, right? So you're planning a Manova, you want to do some kind of multivariate analysis. When you're selecting your dependent variables, you need to select them so that they are minimally related. By that I mean you want them all to be related to the independent variable. At least you want them to be affected by the independent variable. But you want them to be as minimally related to each other as possible. Now, if the IV is impacting all of them, then it's likely they're going to be related to some degree, but you want that degree relationship to be small, at least as minimal as possible. You want to avoid things like multicollinearity. If your dependent variables are really, really related to one another and very correlated, it's actually going to reduce the likelihood you're going to be able to find any combination of variables that maximizes group differences, because all the variables are overlapping one another. And if by chance you happen to have DVs that are correlated with one another, one solution is to use this Roy-Bargmann procedure that we'll talk about shortly, which helps to control for that overlap. The order with which you put the variables into the Roy-Bargmann procedure is going to matter. Your most important variable should go in first, and then second most important, and so on going forward. So that order matters. So theoretically, you need to think about, even though you're picking all these dependent variables, you still need to have an idea of which DV is the one that's theoretically most important, all the way down to the least important, when trying to decide the order for this Roy-Bargmann procedure. And hopefully it doesn't need to be said, but I'll say it anyway, that when you're going to generalize from your sample to a population, realize that your generalizability is limited to whatever population you sampled from. Sometimes we overshoot things. We collect the data from a very limited population and try to make statements and generalize sort of beyond the population that we were actually targeting. So try to avoid that and try to understand who your population is, where are you drawing them from, and when you go to generalize your results, do so to that specific population. I'll give you an example. So much of what we learn in science, especially with psychology, is done on undergraduate students. And yet when we go to talk about the impact that some study has on the population of interest, we usually generalize beyond those undergrad students and forget for a second that the population that we are using is limited. Limited in the sense of that all kinds of people go to university, but they're limited in the sense of they're not going to be like people who did not go to the university for various reasons, and there's going to be a portion of the population in general that are not going to be represented by those undergraduate students, whether that's because of age or because of education or because of their background that allowed them to go to the university. Whatever it is, we tend to overstep and state things about a more general population based on a narrow population of undergraduate students. That's sort of an issue, and it could, in part, be contributing to why it's we're finding it difficult to replicate studies and things from the past, because we're trying to look at a more broad population now than we did then, and it's not quite matching up. Or that university students have changed over time, and they're just not responding the same way to these same studies that they used to. Anyway, so remember, generalize back your population, which means you actually need to know who your population is and have a very clear idea of, when you're getting subjects into your study, who are they and where are they coming from, and how are you defining your population? All right, so let's get to the actual assumptions. I mean, those last couple slides, they were assumptions, but they're really more about theoretical assumptions, things that you need to make sure you do so that you can theoretically, so you can actually make theoretical claims about your data, about your analysis. So these are more in terms of actual assumptions. When it comes to sampling and power, we're assuming that no missing data. So when you have an ANOVA and you have groups and you recruit people to come in, you say you randomly assign people to a different condition, if someone doesn't show up and they don't have a score on the dependent variable, people don't think of that often as missing data. It's just someone didn't show up, so either recruit somebody else to replace them, or you have just some unequal n or something. With Manova, because you have multiple DVs, it's possible for someone to show up but not have scores on every dependent variable. It may have skipped some things in a survey or something, so you don't have every score. So missing data becomes more important here in terms of you need to deal with it in order to make sure that it's not going to wreak havoc or cause issues. One problem that's not listed here is in terms of generalizability. If you're sampling from a particular population and trying to get representation of different subgroups within that population, and people don't show up to your study or don't answer certain questions, you're likely to be missing some of that representativeness, whatever word you like. So another sort of more mathematical issue is that if you have unequal samples, again, you're recruiting people, they're coming into your study, but you're getting a different number of people in different conditions. Unequal samples cause non-orthogonality. Now, we talked a lot about in 485 this idea of orthogonality and how if you have equal n and orthogonal sort of predictors, then it's a very clean sort of analysis. Everything sort of adds up nicely. Your between plus your within ends up equaling your total, and that's fine. But in real life, we oftentimes don't have perfectly equal n. So there is, this unequal samples causes an issue with how the sum of squares get computed. And there's different ways of handling this. There's actually more than these two, but in general, you have to decide whether or not you want to use type 3 sum of squares or type 1 sum of squares. So type 3 sum of squares are basically the defaults. When you actually, at least in SPSS, it's a default. Now, when you go to places or to programs like R, it's not the default. The default, I believe, in R is type 1 sum of squares, and you actually have to include additional syntax to tell R to run type 3 or something like that. But I guess it depends on the package that you're using, but the few that I've seen, most of the time, they do not default to type 3 in R, but SPSS does. So SPSS assumes that you meant for your groups to be equal, like you're going to recruit people to be equal across the groups, and it just happens that different numbers of people showed up, but the differences in the n of each group, well, those differences don't matter. So you want to ignore it and actually compute things like the grand mean based on the marginal means, so that each group contributes just their mean. The size of the group doesn't matter. This is more like the Senate model. Doesn't matter what size the state, what population the state is. Every state gets 2 senators. So same thing with type 3. Doesn't matter how big the groups are. Each group contributes their marginal mean to the estimate of the grand mean, and when you're sort of estimating the sum of the squares and those deviations. With type 1 sum of squares, the group size, those differences in group size actually matter. You actually want to use the differences in group size as information when you're running the ANOVA, or in this case, Manova. So what that means is that each mean that gets contributed or gets used to compute the grand mean and to actually run the sum of the squares is actually weighted by the sample size. So this is sort of a weighted means approach. So we're actually going to weight each one. So those groups that are larger get a larger weight and therefore contribute more to the estimate of the population. The grand mean and stuff, so that it actually has an impact. It actually pulls the estimate of the grand mean closer to those larger groups, and it's going to impact the size of the sum of squares. Anyway, so it may not be something you thought of before, but you may come into an example. I think there's actually one in the lab where a group being substantially larger may actually mean something. The fact that there are more of them may actually be important, and you actually don't want to ignore that. You actually want to use that information and run your sum of squares, run your ANOVA or Manova using sum of squares that actually reflect that difference in sample size. So going back to, or continuing to talk about sampling and power, at a very minimum, very low level, this is not just about power alone, but also just about mathematical, the being able to mathematically compute some of the things we need, like these different matrices we're going to talk about shortly. So at a bare minimum, you need to make sure that the cases in your smallest cell, the smallest group, smallest cell in your design, the number of cases in that cell should be larger than the number of DVs you have. So if not, if you have less cases than DVs, what could happen is that those cells can become singular. And as we're trying to compute things like the different effect matrices and error matrices, it may mean that those matrices cannot be inverted, and therefore the analysis cannot be completed. You may actually get an error if you're trying to run this in SPSS saying, error cannot invert matrix or something like that. If you just have about the same number of cases as DVs, or just barely more than DVs, it's still a problem in the sense that you may end up violating this assumption that we'll talk about shortly, called the equality of covariance matrices, and it may mean that you have some biased results and other issues because you're not meeting that assumption. So you got to think about it. If you have 5 DVs but only 2 cases in a cell, or even if you only have 3, 4 cases in a cell, you actually have less cases than you actually have DVs. That you're likely to violate all kinds of things. The variance and covariances in that matrix are likely to be all kinds of crazy because it's not enough people for those things to stabilize. So because that group's going to have a wildly different estimate of variance and covariance, you're likely not to see that it's sort of homogeneous with other groups that are larger. So that's why it may lead you to sort of rejecting your homogeneity of covariance matrices assumption. So it's not good. If you have a small, additional problem is you have a small case to DV, not ration, but ratio. I don't know why. It's an autocorrect or something on here. So let's see, it's just not ration, but it should be just ratio. Forget the N there. All right, so a small case to DV ratio will mean that you also have low power, right? So if you have more DVs than cases, then it's likely you're not going to have enough power to find a significant effect anyway. And you should use things like G-power or something to estimate the number of subjects you actually need to find your effects. And the trick there is G-power only looks up things univariately, only computes things univariately. So if you know you have multiple DVs, look at the DV that has the smallest effect size across your groups. And if you use that effect size to compute your N, then that effect will be significant as well as any other effect that's larger. So that's why it says use G-power using the DV with the smallest effect, and that'll ensure that everything comes out significant as you sort of plan out your study. Let me erase the DVX. All right, moving on. So in the slides you have, it gives a little more information on this, but I don't know if that's as important. Just understanding that the way that your DVs actually relate to each other can also have an impact on the power of the Manova. So the power of Manova also depends on how those DVs relate to each other. So again, if the DVs have sort of minimal correlations with one another, it's going to have very little impact on the power. The more they become related, the more they become correlated with one another, the more it can impact power. And there's certain types of relationships, like when they're negatively correlated versus positive, and all kinds of stuff that can actually increase or decrease power. So that's something you can look in the Tabashing and Fidel book, and they give a little more information about that if you're interested in understanding what that is, or if you come across a case where your DVs are correlated, you may want to look into that section to see in what way are they correlated, and is it actually negatively or positively affecting the power of your study. Generally, though, as a general rule, the more complex a design or an analysis becomes, the less power it has. And that sounds sort of odd, but as things get more complex and include more and more dependent variables or more and more types of analyses, or more, more groups, more dependent variables, the power is limited, because even though you've diversified your ability to find differences, which sounds like it should increase power, so you're able to look in more places and have more of sort of backups for differences between groups across different DVs, the actual significance of each of those tests actually is lowered, because you have actually less power to find those things. So it's a weird sort of trade-off. So based on an analogy that was given to me as a grad student from Don Butler, who used to be an instructor here before he retired. He taught 524 this class, and actually I don't think he taught 524. He taught 520, which was the sort of mathematics behind 524. So it was the geometry of multivariate statistics course that we used to offer until he retired. Then we stopped offering 520 and instead now offer 534. But at one point he was talking about this analogy between sort of complexity and power that had to do with sort of keys. So let's say you've lost your keys. Now everyone loses their keys every once in a while. Sometimes you're spending a lot of time looking for your keys, and people always say really dumb things like, well, it's probably in the last place you look. Well, of course it's in the last place you look, because once you find them, you stop looking. If you found them and kept looking, that'd be very strange. So of course it's going to be in the last place you look. Anyway, the idea so you've lost your keys, and depending on how much information you remember about the last time you had your keys or where to look for them, the more likely you are to find your keys. So let's say you lost them and you know that your keys are someplace in your house. Now your house, in this case, in this scenario, has many rooms, many places, bathrooms, kitchen, bedrooms. I don't know, this looks like it probably has an attic, maybe a basement. I don't know, lots of places to look. Okay, and let's say that you know it's in your house someplace, but you really have no idea where it is in the house, but you suspect it's there someplace. The last time you remember having your keys was in your house someplace. Okay, if your keys are in your house and you are correct, then you will likely find them, but it's probably going to be kind of difficult. It's probably going to be a challenge to find them, even though if they're in your house, you probably will eventually find them. If, however, your memory is slightly better and you remember that the last time you saw them, you were in your bedroom, right? So one particular room in your house, so not the whole house now, but just one room, your chances of finding it. So again, assuming that your keys are there. Now, so if your keys aren't there, let's say you left your keys at work, none of this stuff matters. But if you really did leave your keys in your house, then knowing that will actually help you find them. But if you know that your keys are in your room someplace, you're actually more likely to find them. You've now narrowed it down. You're more likely to find the keys. But if you instead remember, hey, I think I remember putting my keys in my nightstand. So I've now gone from the whole house to just one room to now one very specific place in the room. You're actually more likely to find your keys. Now, this is assuming that your keys are actually in your nightstand. So if your keys are in your nightstand, you're more likely to find them if you know they're in your nightstand. But if your keys are in your nightstand and all you remember is that they're in your room, you may find them, you're less likely. If your keys are in your nightstand, but you only know that they're in your house someplace, you're going to look through everything, again, you might find them, it's even less likely you're going to find them. So the way this analogy works, if you think about the house like Manova, okay, so you're looking, the different rooms in this case are the different dependent variables. So you're giving yourself more places to look, right? But because there are more places, it's still going to be harder to find. Okay, so there's more places to look, and the trade-off is something like this. If I think my keys are in my nightstand, but they aren't, I can look all day in this nightstand. I'm never going to find my keys. So that's the trade-off between this nightstand analogy is, If the keys are there, you're more likely to find them, but if they're not, then you only got one shot to find them and that's it. While in the bedroom, I may think, that the keys are in my nightstand, but they could be in the other nightstand, or they could be under the bed, or they could be somewhere else in the bedroom. So even though this represents a more difficult, more challenging way of looking for keys, it allows more options for where those keys might be. So here, if the keys do not exist or were not left in the nightstand, there's no way to find them, period. However, if the keys are in the nightstand and you're doing something like looking in your whole bedroom, it's going to be harder, right? Less power. It's going to be more difficult to find, but you didn't exclude all other places where they might be somewhere else. So you actually have more places to look. Right, so it's one room, but you're giving yourself more groups, more comparisons with which to compare them, which, more places to look for your keys in that room, which might mean that even though you thought it was in your nightstand, maybe it's under the bed, and you're able to find them, which you couldn't do using just the nightstand. So again, the analogy here is something like this. The bedroom is more like an ANOVA, and the nightstand is more like a t-test. So t-tests are very specific. I think this group and this other group, these two groups are different on this one dependent variable. If that difference exists, if those two groups are different on the dependent variable, then this is the best case scenario for you to find it. It has the most power. Right? But if it's not there between those two groups, this won't find it at all. So even though ANOVA has less power to find that difference in t-test do, it gives you more places with which for group differences to be than in that one specific comparison. Okay? Same thing with Manova. If your keys are not in your bedroom, right? So the analogy there is if the differences between groups are not on that one particular dependent variable. So you've added more groups, but it's still only one place. It's still only one dependent variable. You're never going to find the keys. Where Manova is more difficult, more places to look, means less power, but it still allows you more options, more places to find group differences on multiple dependent variables than if you did it with the ANOVA or with the t-test. So there's a trade-off. And you see as you go down from ANOVA down to t-test, you're actually getting more powerful as it goes down. But again, this is assuming that your keys are where you think they are, or that the difference, the effect you're looking for is actually there. It actually exists. Okay, if that's true, it's more powerful. Your keys are actually in your nightstand, but you look through your whole house. It's going to be more difficult to find them. Your keys are in your nightstand, but you look in your bedroom. So it's going to be easier than Manova, easier than looking in the whole house, but harder than looking in the nightstand. And if the keys are in the nightstand and you actually look at the nightstand, that's your best chance of actually finding the keys, right? So this is the best case in which you're actually going to find the difference you're looking for, which is why in lots of places in Tabashik and Vidal, they say if you have a specific hypothesis, I think this group is different than that group, you should test them directly with a t-test before you sort of bury it in some overly complicated but less powerful Manova or even an ANOVA. Test it directly, and then if you want to do some exploratory, analyses looking at other DVs and other groups, then sure, do a Manova, but make sure you get those hypotheses tested that you want before you start burying it and everything else. All right. So another assumption of Manova, something called multivariate normality. So I said earlier that just like with every general linear model that we've talked about so far, regression, ANOVA, we're assuming things are normally distributed. But because we're getting more and more dependent variables together on the sort of one side of the equation, we're assuming that they actually share a joint normal distribution space, that they're actually multivariate normal. That not only is each individual one normal, that when you combine them together, you get a normal distribution. It's just a three-dimensional or n-dimensional space. So instead of thinking of it as just a unidimensional sort of normal distribution, we're now thinking about the distribution sort of in more dimensions. Okay, so it's now a multi-dimensional space. If your the number of subjects in your smallest cell is larger than 20, you can probably ignore even really testing for multivariate normality. Probably doesn't even matter that much. So if the smallest cell is over, equal to or greater than 20 cases, then it's robust to violations. You can probably not even bother to look at the tests. And even this is even true when you have unequal n. It really doesn't matter. The tests are robust to it, so you can probably ignore it. If you have smaller unbalanced designs, then the assumption is assessed based on researcher judgment. So what that means is that you may want to investigate you actually want to look at the distributions. Even just looking at them univariately, you may start to figure out that there are issues with normality on some of the variables that when combined are creating a multivariate abnormality, non-normality. But there's also, back up actually, there's no test, no real easy test for looking at multivariate normality. I'm trying to think if there is. In some other programs there are. Well, the idea is that if you have sort of small unbalanced designs, you're already in some issues anyway because of the power is going to be low. But you may want to start looking at the actual distributions. Anyway, this is what a bivariate normal distribution looks like in a sort of two-dimensional picture. You can sort of see there's an x here on this side. You got y going that way. And combined, this is basically a normal distribution going along the y and another one going along the x. And combined, they make this sort of cone shape that you see here. And I'm going to show you this this other example, this little more interactive. All right, so here is a bivariate normal distribution. It shows the means of x and y, the variance is x and y, and then this last one down here, I believe, is rho. So I'm assuming this is actually impacting the correlations between the two of them or something, but I'm not going to worry too much about that one because I want to just show you how changing the distributions of x and y can actually affect the look of the bivariate normal distribution. So right now, if you look at this, it's a cone shape, basically right dead center. That center being the sort of mean on x and mean on y. Actually, this is y. Mean on y, mean of x. Right? So it's basically a standard normal distribution for both of these, so the mean's at 0 on both. Okay. All right. If we start to move, say, the x mean sort of lower, what you start to get is that there's still basically a bivariate normal distribution. It's just that now it's not in the center. And this could actually be a sign that maybe x is skewed, right? You got a peak here, it's going out that way, this stuff's cut off on this side. So maybe some skewness on x, but as I look at x, it looks like it's obviously, something up there. The peak here is sort of offset. But if I look at y, it's actually hard, you can't tell there's anything even wrong. Y actually still looks perfectly normally distributed. Okay, so let's say I put x back to 0 or close to it again. All right, so now we're back at essentially, let's say, normal distribution from the beginning. Okay, everything looks the same all the way around. Very uniform normal distribution here. If I start to affect, say, the variance instead, I can raise it up. Again, when I look at y, so I've changed x, y looks the same, but now x looks very different. Okay, and the whole area starts to look sort of oblong instead of being sort of more circular. Same thing if I affect x this way by actually making its variance very small. You see, is looking at the y plane, that actually looks perfectly normally distributed. If you look at the x plane, you can see it's now sort of skinny, and you might think it's sort of leptokurtic on the x side, so this may make a bivariate distribution that is non-normal. As a combination, it's like this weird, almost like looks like a shark fin or something. So this is not as normally distributed bivariate normal as it was when they're both, they don't have to be the same variance, but, should be pretty similar. It should make the sort of cone shape that you see here. Okay. Hopefully that helps to make it make more sense. You can see what a multivariate normal distribution is. It's basically the combination of the variables, each of them being roughly normally distributed, combines together to make a multivariate normal distribution that's covered by these sort of area, that's shown by these sort of area plots here. All right, let's go back to here. All right, let me come back to the window. Okay. So we're also assuming things just like with ANOVA and regression and everything else we talked about so far, that there's no outliers. The people in our study are supposed to be there. Now, whether that means they are sort of qualitatively an outlier, like, you're only recruiting men and somehow a woman showed up to the study or something like that, that could be an outlier, but also could mean that they respond in a different way, which may indicate that they don't belong in the population that you're recruiting. For instance, I remember when I was an undergraduate, a friend and I were doing a research project, and he was looking at the Stroop test, where you name the colors of words on the wall, and this guy, he was supposed to, again, everyone that comes in is supposed to name the color of the ink and not read the word. So this guy came in, everyone was doing it in like a minute or something, a real short time to read through all the words. And this guy came in and he was there for, I don't know, like 20 minutes or something like that. It took him a really long time to go through the study. And so not only was he sort of distributionally an outlier, he was sort of way, way, way above everybody else. But at the end of the study, when he was getting ready to leave and stuff, we asked him some questions like, "Oh, it seemed like you're, struggling with, being able to name the color." He's like, "Oh yeah, I'm colorblind." So we realized then the importance of exclusion criteria from studies. If you want people to be able to name colors, color blindness is obviously going to impact the ability to do that, and they're probably not part of the population you're trying to recruit from. So even though he was distributionally an outlier, he really was qualitatively one anyway, and we ended up not using his data because of that, because he didn't really belong to the population we were intending to sample from. Anyway, so we're assuming things like linearity as well. Your DVs, your CVs, and your DV and CV relationships should all be linear. If they're not linear, like you got curvilinear relationships, other things, Manova, just like ANOVA and other places, are not going to pick up on those types of relationships. So nonlinearity actually may reduce your power. So the groups may be different, but in a nonlinear way. So when it tries to linearly combine the DVs to differentiate between the groups, it's not going to be able to do that because the differences are not linear. So you actually can reduce power and stuff. And if your covariates are not linearly related to your DVs, then your covariates are not going to adjust the error very much, right? You want them to sort of reduce error and sort of make the test more powerful, and it's not going to be able to do that if it doesn't have a linear relationship with the DVs. We're also assuming that the DVs are not multiclinear or singular, so no multiclinearity or singularity. You don't want your DVs to be redundant. Now, they're going to be related to a certain degree, and that's fine, because it's sort of hard to, even just randomly correlated is going to be a thing, right? There's going to be a little bit of relationship between them. But you don't want them to be too correlated. Now, again, there's always a question, what does too correlated mean? Well, it's sort of the same idea. Once it starts getting into the higher sort of correlation values, you're getting correlations that are indicating that the DVs in this case are redundant. There's really no point in having, especially in getting to the singularity thing, they're basically the same variable. You don't need to have them in there. They're not really adding anything different than the variable that they're repetitive with. So, and the only reason why this becomes more interesting in Manova is because you have multiple groups, and each group has multiple DVs. So really the multiclinearity singularity needs to be tested in each cell of your design to make sure that you're not seeing any sort of collinearity pop up in any of those cells. So because you have multiple DVs, I can check for multiclinearity. You need to do that in all the cells of the design. So one of the last assumptions is something called homogeneity of covariance matrices. Now this sounds complicated, and actually might be sort of complicated. It may require you to think about data in a different way, a way you haven't really thought about it before. But as we're sort of thinking about more and more things in a sort of matrix framework, the homogeneity of covariance matrices really is just a matrix extension of the homogeneity of variance we had in ANOVA. So this is basically a multivariate version of homogeneity of variance. So instead of assuming that the variances are equal across groups, because then we just have one dependent variable, therefore it's just one variance in each group, and we can see that they're equal, like with the Levene's test or something, or Fmax. Here, we're actually assuming that the variances and covariances between the DVs are equal across groups. So that means we're actually computing a variance-covariance matrix for each between the DVs for each group, and then comparing those matrices across groups to see that all the corresponding parts are roughly equivalent across them, or homogeneous. So it assumes that variance-covariance matrix in each cell is approximately equal. That's the sort of plain way of sort of saying it. Another way of thinking about it theoretically is that it assumes that each cell is sampled from the same population, so we can take the variance and covariance matrices and pull them together to make a common error matrix. Now, if you replace some of those terms and sort of state it more univariately, it sort of sounds familiar, at least I hope it does. So when we're looking at homogeneity of variance, we assume that each cell is sampled from the same population so that the variances within cell's variance can be reasonably pulled together to make a common error term, right? So that's what it was for homogeneity of variance. All we're doing is extending that out to a matrix of variances and covariances between the dependent variables. So let's take a look at what that looks like. Okay, so let's say we have three dependent variables, whatever they are. This is just generic. We have three dependent variables, and we want to take those three dependent variables and we want to compare group 1 with group 2. So this is essentially a tau squared, a multivariate extension or multivariate version of a t-test. Two groups, and we're comparing them on three dependent variables. So before, when we were doing just an ANOVA, we only had one DV. So we really only had to worry about this single variance here, right? So that variance and this one were really all that we cared about, because that's all we really had. One dependent variable, one variance. So we had a variance for group 1, variance for group 2, and we assumed that those two were roughly equal. And that was basically the homogeneity of variance assumption when applied to something like ANOVA. Well, now we have, instead of just one variance, we have three of them, right? Those. I have the same variance for dependent variable 2 here and dependent variable 3 there. So I have those three variances. And part of what this homogeneity of covariance matrices assumption is assuming is that, yes, these three things should be equal. Right? I'm assuming that these things are all equal to each other. Okay? So that's one assumption, and one part of the assumption. Now, as you're probably realizing, or looking here, I also have covariances. So this is the covariance between. That's strange. This is supposed to be orange. It looks green too. Hold on, let me do something different. I also have that, and I have another covariance down here. So this is the covariance between DV2 and 1. This is between 3 and 1, and then I have another one here. There's the covariance between 3 and 2. I have those same covariances on the other side. I have the covariance between 2 and 1 for group 2. For here for 3 and 1 for group 2, and for 3 and 2 for group 2, I have those same covariances. Now, up here, these just repeat. So you don't really have to worry about these because the covariance between 2 and 1 is the same thing as the covariance between 1 and 2. So we know they're written here. These are just repeats. So you don't have to think about them all over again. Actually, wait, move that up here. These are repeats. You can actually see it. Okay, they just repeat what is down here on the bottom. Same thing here. These covariances here are just repeating what is down at the bottom. So we don't have to do, all 6 of them in this case, just these, we said the word about these 3. So what I want to see is that this covariance is also equal to this covariance. So we're assuming that those 2 things are equal to each other. We're assuming that the covariance here is equal to the covariance there. Right, those should be equal. We're also assuming that this covariance should be equal to that covariance. So what the homogeneity of covariance matrices is doing is saying, I'm assuming that the variances among these 3 variables and their covariances are equal across groups. If I'm doing this as a Manova with more groups, well, there's just more groups. I would have a 3rd version of this, and a 4th, a 5th, a 6th, how many groups there are. I'm going to have another matrix for each group, and I'm assuming that they're all the same across all of the groups. All right, so in terms of testing that, it seems like it'd be crazy to try to do that. There's no like Fmax by hand, easy way of doing a test for homogeneity of covariance matrices. So typically when using SPSS, we're going to rely on something called the boxes M test. And if your samples are roughly equal, it doesn't have to be exactly equal, but they're pretty close to each other in sample size, you can probably ignore boxes M altogether. It doesn't really matter because the test is robust to violations of this boxes M test. If you have unequal samples and you look at the boxes M test and it's below 0.001, so sort of like Levine's test, this is a very conservative test and it'll likely reject things more often than it should. So use 0.001 instead of 0.05. And if your samples are unequal and you evaluate boxes M test at alpha less than 0.001 and it's violated, then your test is questionable and interpreting the outcome may be biased. You may have some bias in your sample that is making the F test significant when it shouldn't be, or vice versa. Okay, so you may want to be careful with how you interpret your output. One way around this, or one thing you can do, and we'll talk about this more in a little bit, is use a stricter test criteria instead of Wilks. So we'll talk more about the different test criteria, what that means, which ones are more or less strict and all that stuff. But just the idea that Wilks is a sort of standard test that we use for looking at this, but you can use something like Pillai's trace instead of Wilks that is more conservative. And if it's still significant with Pillai's, then it actually might help to correct some of the issues with sort of violating this boxes M test and violating the homogeneity of covariance matrices assumption. All right. The last assumption here is talking about if looking at sort of Manova, as this is sort of an additional thing. This is beyond just Manova, but if you're looking at a Manova and you want to assume sort of homogeneity of variance, which is there at the top. The same thing is for ANCOVA, just the relationship between the covariate or covariates and the DVs should be the same for all groups. All right, so we're assuming that the relationship, the regression line, the linear relationship between each CV and the linearly combined DVs, this sort of super composite, smart composite, is roughly the same for every single cell of the design. And you're also assuming that the covariates are measured at a reliability of 0.8 or higher. That's pretty standard. tend to think of a reliable variable as one that's measured at 0.8 or more. So we want our CVs to be at least that high. This also applies to DVs when you're doing this Roy-Bargman step-down procedure. The reason why is because there's different steps. In step 1, you're doing a ANOVA. You do a ANOVA on the most important DV. Step 2, you go to the second most important DV and you use the first DV as a covariate in an ANCOVA. So still sort of treating it sort of univariately, but we're now using each, in each subsequent analysis, each DV becomes now a covariate for the next DV. So if that's true, and you're going to be doing that sort of procedure, then we're also assuming that the dependent variables are measured with a reliability of 0.8 or more. Okay. All right, so this is about out of time, and since I don't really want to start into the equations with very little time left, we will talk about the equations, the sort of methodology behind this without going too much into a whole lot of craziness. We'll get just a little bit crazy with some matrix equations and try to get through as much as we can in the next class, and try and wrap it up as much as possible. And any additional information that we need to cover, I'll likely sort of put together some supplemental material to sort of put out. You guys can to help you sort of understand things, but just so we can move forward and get on to profile analysis, we'll likely take one more day to look at Manova and then sort of move on. All right, thanks.